Now let's look into the more concepts of random probability or probability distributions, which belongs to the random variables. So let's begin with the expectation of a random variable. Expectation of a random variable. So in probability theory, the expectation of a random variable RV is a measure of its central tendency. That's it. In probability theory, basically that too belongs to random variables, and then probability distribution expectation is nothing but it is one of the measure of central tendency. We have seen the measures of central tendency in our descriptive statistics, mean, median, mode. Similarly, expectation is one, and that belongs to probability theory. In probability theory, the expectation of a random variable is a measure of its central tendency, representing the average value of the RV. Average value of the RV. That's it. That's what is your expectation. So expectation represents the average value of a random variable. So expectation of a random variable tells the expected or average value it takes. So the expectation of a discrete random variable we will calculate some other way, and the expectation of a continuous random variable would be some other way. First, let's see expectation of a discrete random variable. The expectation of a discrete random variable capital X with probability mass function P of X, and which is defined as this. So the expectation of a discrete random variable can be represented as this. Capital X belongs to Sx having probability mass function P of X. Hence, how do we denote that expectation? So expectation of X will be denoted this way. E of capital X is equal to summation of X belongs to sample space of capital X, and it's X times P of X. Each value of random variable X multiplied by probability of respective respective value of X. So that's what is the expectation of a discrete random variable. The expectation of a discrete random variable, it's is equals to E of X is equals to summation of X belongs to Sx. Each value which is part of the respective sample space of the random variable capital X is multiplication. What you have to sum up, what you have to sum it, the multiplication of respective value of the multiplication of value of X with the respective probability of value of X, that is X times P of X for each and every value of X in their in respective random variable sample space. Then for a continuous random variable, random variable, capital X belongs to Sx. Again, for continuous random variable with capital X with probability density function PDF, P of capital X is equals to F of X, the expectation is defined as obviously integration. So E of X is equals to integral X times P of X, same function, X times P of X multiplied by dx, because here we will be looking in with respect to the interval. We'll see the density, we'll see the area it's spreaded. So that's the reason we are doing the integration. So whereas here the summation of X times P of X, and here integration of X times P of X with respect to the dx. So now, so here the probability density at capital X, that's our random variable, and small x is our individual value of random variable capital X. The definition applies to functions of random variable 2. Example, it can also be if these definitions, of whatever definitions we have seen here, we have defined with respect to the random variable, but we also can apply the same definition even to the functions of a random variable. That means you have a function of f of capital X is equals to capital X square plus 2. You can apply the same formula to calculate the expectation of a function of random variable. So note that expression this expression is with respect to the distribution P of f of x, not probability of capital X, it's P of f of x, respective function of the respective random variable of, okay. So expression is always with respect to the probability distribution P of capital X of the random variable, and often written as EP of X. If it is if you have to calculate the expectation for a function which consists of a random variable, and this is how we express it. Now let's look into one example. Expectation. So example, suppose we have a binary classification problem where X is a random variable representing the probability of an image containing a cat, and P of that's probability of X is the probability mass function of random variable capital X. So now we can compute the expectation of capital X. Let's compute it. So let's compute the expectation of a random variable capital X as follows. So E of X, or this way, E of X is equal to 1 times P of X is equals to 1. That's the first value. And similarly, as it is a binary classification, you will have 0 and 1. Simple. Then you have 0 times, because X times P of X, correct? So 1 times P of probability of X at 1, and then 0 times probability of X at 0. That's it. This is your expectation for the respective binary classification problem. So few more formulas we have here for the expectation of sum of two random variables. E of x plus y is equals to E of x plus E of y. It's like that. So E of x plus y is equal to, if you want expectation of sum of two random variables, then it's sum of individual expectations of the random variable, okay. Then E of x plus y will become E of x plus E of y, expectation of x plus expectation of y. And if you want to know, this is what the proof is. So let's take the new random variable, that's z is equals to x plus y. Then you have to calculate E of z. E of z, again you have to apply the same formula. E of z, the small z, the value of individual value of z belongs to sample space of the z, and z times P of z is equals to z, and you apply and you do the respective derivation, respective you derive the whole theorem and finally you'll get E of x plus E of y from this. And that's what the proof of it. So expectation, the point to be remembered is expectation of sum of two random variables E of x plus y is equals to E of x plus E of y. And the most important point when you calculate expectation of sum of two random variables, one is the x and y need not be even independent. They don't need to be independent. Even if they are dependent, still the formula can be applied, and they can be discrete or they can be continuous. Okay. So next, a few more rules of expectation. So first one, expectation of a scaled random variable. This is how, if you want E of alpha times x, and the expectation, if you want to calculate, it will become alpha times E of x. So you have a random variable, it got scaled up, then it's pretty easy to calculate. So alpha is any real valued scalar. Okay, you can calculate expectation of a scaled random variable very easily. Then linearity of expectation, if you have, again you apply the same scaling to the both random variables, and you want the summation of the scaled random variable expectation, then this is how E of alpha x plus beta y is equals to alpha times E of x plus beta times E of y. So alpha and beta are real valued scalars, then a linearity of again expectation. So but this time it's for the functions, of random variables, functions of not random variables, not just random variables. Then same, it applies in the same way. So E of alpha times f of x plus beta times g of y is equal to alpha times E of f of x plus beta times E of g of y. Then expectation of f and g are arbitrary functions here. Then expectation of product of two independent random variables, but this time independence and dependence is matter. So the expectation of product of two independent random variables, that's E of xy is equals to E of x times E of y. Then law of the unconscious statistician, we call it as a lotus law of the unconscious statistician. Given an random variable x with a known probability distribution p of capital X, and another random variable y is equals to g of x for some function g, then E of y, expectation of this y is equals to E of g of x, obviously. So then you can calculate this summation of y belongs to sy, and y times py, y times p of y. So this is what we call it as a law of the unconscious statistician, lotus. And last one, rule of iterated expectation. So E p of x is e subscript p of x is equals to e of ep of x given y, is what the rule of iterated expectation. This is what is called rule of iterated expectation. Now let's see one example, and let's wrap up this expectation concept. So this time example 2. Suppose we have a language model. That generates sentences, and x is a random variable RV representing the number of words in a generated sentences. Let me put it here. X is a random variable representing the number of words in a uh, generated sentence. So, and f of x is equal to probability density function. Obviously, it's a continuous random variable. So, f of x will become the probability density function. You can also show it as p of x. P of x is equals to small x. So now we can compute the expectation of x as follows. So e of x is equal to, of course I can put the integration symbol here, so I don't know how to put that. Okay, let me say integral of x times x times f of x dx. So where we integrate over all possible values of x, that is the number of words in a sentence, the expectation gives us the average number of words in a generated sentence. The expectation of a random variable is a useful measure in a probability theory, as it summarizes the behavior of the random variable with a single number. It's often used in statistics and machine learning to compare different models or to evaluate the performance of a model on a data set.